Okay, yo, I was editing the video and then the first part accidentally got like cropped out and I can't get it back anymore. But basically, this video is gonna be going over the 2019 AP Physics 2 free response question number 4, which is about a bubble. So weird, but yeah, I just wanted to put this in just to know that we're not just like doing. I just didn't want to jump straight into the video and like be like, oh, here's a problem y'all didn't even know. So I'll put the problem link in the description below, and yeah, hope y'all enjoy, and happy Thanksgiving. A student notices many air bubbles rising through the water in a large fish tank at an aquarium. Part A. In the figure below, the circle represents one such air bubble and two incoming rays of light. A and B are shown. Ray B points towards the center of the circle. On the diagram, draw the paths of rays A and B as they go through the bubble and back into the water. Your diagram should clearly show what happens to the rays at each interface. So, we have Ray, this is her bubble right here. Ray, oh my gosh, why are my markers like dying? A, and then Ray B, like so. Right, and Ray A is directly towards the center of the circle. And outside the air bubble is water, and inside is air. So let's take care of this Ray A first. So it's directed towards the center of the circle, and therefore, at the point of contact right here at the surface, the angle of incidence is actually going to be 90 degrees. In order for any refraction to occur, two requirements must be met. One, the mediums for which the rays traveling through must have different optical densities. And second, it cannot approach the boundary between the two mediums with an angle that is 90 degrees. It must be some other arbitrary angle. If it's the 90 degrees, the only thing that will happen to this ray, if anything, is going to be that the speed of the ray as it travels through this medium is going to change. In this case, it's going to increase, but otherwise no refraction. So we're pretty good. We can just redraw our ray straight through. Nothing stranger there. However, for ray number B, the first thing I like to do in geometric optic problems is to establish a normal line. So a vector that is perpendicular to the surface between the two mediums, right? So if we redraw this ray B right here, I'm going to put it closer right here. If we redraw it like so, you'll notice that it's going to deviate from this normal line by angle. Let's call it theta sub 1. So that's a theta sub 1 right there. It's clearly not 90 degrees, right? So the thing that happens to it as it emerges from going from water to air, we need to consider something called Snell's law, which is given by this equation right here. Say that our first medium is going to be water, so this is water, and then our second medium is going to be air. So for water, the thing is that it's more optically dense than air. So if it's more optically dense, so this is more optically dense, that means the index of refraction is going to be greater for water, right? Now, what is the index of refraction? So I'm going to go a little bit in depth here. It's a ratio between the speed of light and the velocity of the ray, of the wave going through a certain medium, right? So in water, it's pretty slow. Water's pretty dense, right, compared to air. So for here, this V value is going to be pretty low. And as you can tell, as this gets lower, it's inversely proportional to the index of refraction. Therefore, if it's more optically dense, the ray is going to move through it slower, and the index of refraction is going to be greater, right? So that means this N1 is going to be pretty big. To balance it out, to make this equality hold, the sign of the incident angle is going to have to decrease. And basically what that means, right, it will make sense to you when I analyze what happens when it goes into air. So basically what happens, since this is more optically dense than this is what's going to happen when you redraw the ray here as it pops out. So what's actually going to happen is it's going to refract at this angle theta 2, which is supposed to be greater than theta 1. So let me specify this. Theta 2 is greater than theta 1. Right? And the reason for this is, so air is less optically dense than water. Therefore, we can say the speed of the wave through air is going to be greater. As this gets bigger, the index of refraction for air is going to be less than the index of refraction for water. So this, relative to this, is going to be down. That means the sine of the angle is going to have to increase. And the sine is a function for which theta, if you increase theta, so long as it's between 0 and 90 degrees, it's going to increase, right? So we can say for more optically dense mediums, theta is going to be smaller than for a theta for a less optically dense medium. So that was the conceptual part of it. But basically, you're going to redraw it like so. And then this ray, newly refracted ray, is going to approach this surface right here. Once again, I'm going to establish my normal line like so. Let's call this angle theta 2. And finally, it's going from less optically dense to more optically dense. Therefore, the sine of this new angle over here is going to be less, right? Therefore, the angle is going to be smaller. By the way, the angle is with respect to the normal line. Notice why I drew the normal line is to establish a reference point for this refraction angle. Okay? Part B. The bubble has volume V1. Air inside it has density rho sub A. I gotta use their variables. The water around it has density rho sub W. The bubble starts at rest. So let's just say V naught is equal to 0. And has a speed V final when it reaches a height H. So it's basically from the bottom of the tank, the bubble's gonna go like straight up to the top, right? It's gonna rise to the top. Assume the change in the bubble's volume is negligible. Derive an expression for the mechanical energy dissipated by drag forces as the bubble rises this distance. Express your answer in the terms of the given quantities and fundamental constants as appropriate. Let's draw. So, dealing with conservation of energy, right? Low battery. So the bubble starts here at rest, and then it's going to move up to some point like near the surface, right? So this is conservation of energy. So the first thing I'm going to do is I'm going to establish my 0 point. I'm going to set my 0 point at the bottom of the tank. And so then at the end, so I'm going to redraw a bubble right here. I'm going to have speed V final, and it's going to be at some height H, correct? So let's call this point A, and let's call that point where it reaches height H B. So energy at A is equal to the energy at B. So we need to consider what's going on here. So it's at rest, there's no height, so immediately kinetic and gravitational potential are out. There's no spring. That would be pretty weird. And is there work in? Yes, there is work in, because how did it get moving in the first place to go all the way up? So we can say there is work in on the system, right? And then energy at B. So now it's moving. So as kinetic, it's at a height, since we said our 0 point is the bottom. And also, since it's deriving an expression for the dissipative forces, which takes mechanical energy away from the system, we're going to say there's going to be some work out, right? Due to some drag force. Boom, we're set. So work, the formula for that is F over some displacement, let's say delta Y in this case, it's moving up and down, right? So we know that it's in water, so there has to be a buoyant force that made it go all the way up, right? So the formula for buoyant force is the density of the fluid, which is water, times the volume of the bubble, V1, times the acceleration due to gravity, G. And delta Y, well, it's going from this height at 0 to some height H, so we'll just say H, right, for the change in Y. And then the formula for kinetic energy is 1/2 mv final squared plus gravitational potential, mgh, right, rises to a high H. And then this work out. No idea what it is. So basically, we need to express it in terms of only these given quantities. Therefore, that mass we need to take care of. So what is the mass of this thing, right? it's going to be the mass of the air that's in it. So if we recall the formula for density, let's do this with respect to air. Rho sub A is equal to m sub A over V1, right? Because the volume is the volume of the bubble. So if you solve for m, rho A V1 gives us the mass of the air in the bubble. So we can substitute that in here. So rho WV1GH is equal to 1/2 rho A V1 V final squared plus rho A V1 GH plus work out. So subtracting these two from both sides, we get this equation to isolate work out. And that is the formula for the mechanical energy the bubble loses on its motion up due to some drag forces in the water. So at a particular instant, one bubble is 4.5 meters below the surface. The surface of water is at sea level, and the density of water is 1,000 kilograms per meters cubed. So we know that already. So part one, determine the absolute pressure of this thing, right? So the absolute pressure is equal to the gauge pressure at that point plus the pressure of the atmosphere at sea level, STP, right? For y'all chemists out there. And the formula for gauge pressure is density of the fluid, which is going to be water times G times height from whatever 0 point you set, right? Typically at the surface of the fluid. So substituting in, we get rho water GH plus pressure of the atmosphere, right? And so we have H, we know G, we know the density of water is 1,000, and this is on your formula sheet, so plug and chug. So the part two, the bubble has volume V1 when it's 4.5 meters below the water surface. Assume that the temperature of the air in the bubble remains constant as it rises, so T constant. So immediately, Gay-Lussac's law should apply, or Boyle's law. Wait, hold on, no, I'm tripping. Boyle's law, yep. In terms of V1, calculate the volume of the bubble when it is just below the surface of the water. Okay, Boyle's law. P1 V1 is equal to P2 V2, right? Pressure, volume, where temperature is constant. This is just the ideal gas law, just specified for a certain situation in which temperature is constant. So for this, we're gonna assume immediately that pressure, just to be safe, we're gonna use absolute pressure. Unless it says gauge pressure, use gauge pressure, but if not specified, personally I would use absolute pressure. So we can solve for V2, which is this final V, right, that we don't know. So, okay, so we need to consider the pressure when it is 4.5 meters below the water's surface, right? Because we're analyzing this equality when it's 4.5 meters below, and then when it's actually at the surface level. So, just draw another picture here. So, this is 4.5 meters. This is part one, and then part two is where it's up here, where there's zero height, right? Since I said for pressure, we typically set our zero height at the surface of the water. So P1, we said absolute pressure, so pressure of the atmosphere plus the gauge, which is rho of the fluid, water, GH. And we have the H, that is 4.5 meters. So we substitute that in, PATM plus rho water GH V1 over, and pressure 2, the absolute pressure is just going to be the pressure of the atmosphere, because at that point it's at the zero height level, therefore we don't need to worry about gauge. Excuse me, we're just dealing about it with the pressure of the atmosphere. And that's it. That's the final expression that should give our answer for this final V when the bubble reaches the surface. And we know that it's constant given in your formula sheet. We know the density of water, we know the height, And in terms of V1, and we have V1, there you go. So plug and chug numbers. So if the air in the bubble cooled as it rose, the volume of the bubble would be less than the value calculated in part C. To use physics principles to briefly explain why. Okay, so you can use the ideal gas law to demonstrate this. I would personally go for this. I would show an equation because I don't really like writing a lot of words. And then I would solve for V2 and basically explain that if you want to put this into words, I would say since it cools down, the molecules in the bubble are going to be moving around less, therefore the pressure exerted on the surface of the bubble is going to be less, and therefore the pressure of the water in the atmosphere is going to compress on it more, and therefore the bubble volume would decrease as it reaches the top. So that's an example of what I would say, but mathematically this is what it corresponds to. So that is part 3. So yeah, that is it. That is question 4 on the 2019 FRQ.